Graphs by Gautam Dasarathy.
Thanks for sitting here. This is joint work with Pari Shah, Badri Bhaskar, and Rob Nowak, my advisor, when we all overlapped in Wisconsin sometime. So this talks about sketching methods for covariance matrices and other sparse graphs, but I'll start motivating by the covariance matrix. So what we are talking about is like covariance matrix estimation. Covariance matrices, as we all know, are like truly ubiquitous. You want to estimate covariance matrices for various tasks like PCA or this figure right here is from the Boone lab. I don't know if you can see properly, but this is in Toronto. And what they do is they wanted to map out the genetic landscape of a yeast cell. So each dot there represents a gene, and they try to connect this using the covariance matrix. They threshold the covariance matrix, they get a graph, and then they cluster this graph to find out the functional components of the thing. So we are dealing with large covariance matrices all the time. And when you usually have a lot of data, one standard way of dealing with it is sketching. Like when you are not able to deal with data, you try to project it onto some lower dimensional space such that it preserves some properties, right? And then the sketching has like nice interpretations when from a system point of view. Like for instance, let's say that I'm collecting data and David is the learner. Then I can say that, okay, my data is very structured, so I don't have to send all this junk to David. I can like compress things and send it to him so that he can do efficient learning. And on the other hand, in biological experiments, it might really make sense for you to club things together and perform experiments at this pooled level instead of like doing many experiments at the base level. So that's what we're talking about. And today I'm going to describe a way that you can do sketching for estimating a covariance matrix. And what we have here is you have C1 to Cn, which are like samples from a Gaussian 0 sigma for simplicity. There's no need for this, it just makes things more easier to describe. And a sigma is an unknown covariance matrix. I'll describe that in a bit. And to sketch, we'll have a fat sketching matrix A, where A is m by p. P is the dimension of these C guys. So, and m is much less than p. And so you have like this fat matrix that takes in these samples and makes it smaller. So what you observe is not the C's, but you observe Zi's. So this picture kind of shows you what's going on. And the goal is to estimate sigma from Z1 through Zn. So now you have like these compressed samples, which really don't tell you anything about the covariance matrix ostensibly, and you want to like recover the covariance matrix from these compressed samples. And notice that from this you can never recover Ci because Ci is not sparse itself. It's like just some random vector. So you can't do the compressed sensing trick. Here's a quick observation. If you have these sample sketches, you can work out what the sample covariance matrix of Z looks like. And it just looks like A sigma hat A transpose, where sigma hat is the underlying covariance matrix. And this is like a basic probability calculation if you want. And this suggests like a following stylized problem, which is that given A sigma A transpose, can you recover sigma? Okay? And let me just like make this a little more general. What we have here is now a sparse matrix X, which is a P by P matrix. And like A is the sketching matrix, and what we want to do is recover X from AX A transpose. Okay, so this is like the abstract version of this problem. And in general, this is not possible because A is A is fat and M is much smaller than P. But if X has fewer than, this is more like M choose 2, but you get the idea. If X has fewer than the number of measurements we make, number of degrees of freedom, then recovery might be possible, and we'll see how we're going to do it. So the other part of the title was something to do with graphs. My poster is there for more details, but I'll just like blitz through the rest of it. But the idea is you want to estimate a sparse graph that is, say for some reason, say network tomography or something like that. And what I propose to do is group these vertices of the graphs into some random subsets. So you have like V1 through Vm, these are random subsets. And what you measure is not like say the adjacency matrix of the graph, but you measure this Y matrix such that Yij tells you the number of edges between Vi and Vj. So this is like a coarse level information of this graph. So you can imagine that say you're only like measuring cuts across some coarse regions in this graph. So, and if you look at this A matrix as the ith row of A as the indicator vector for Vi, the vertex set, then this is precisely the same problem, that if you have like Y equals AX A transpose, can you recover X, which is the original adjacency matrix? And it looks like a hardish problem. And this has like other applications. I'm not going to go into that, but essentially like there's a long line of work which is motivated by DNA shotgun sequencing, where they handle something called additive queries, and these look exactly like that. Here's another simple observation, which is that if you vectorize this guy, AX A transpose, then it looks like A Kronecker A times vector of X. So this is, again, from basic linear algebra. And if this is called a Kronecker product if you're from signal processing, or if you're from somewhere else, you call it tensor product, I guess. So this is a sensing matrix. You can think of A Kronecker A as your sensing matrix. I'll use these two words interchangeably. And you want to recover this guy, vec of X, and what you have access to is this guy, right? And this really looks a lot like compressed sensing. You have like a short vector, and you have like a fat matrix, and you have a long vector that is, so I'm claiming is sparse. So, but the problem is that A Kronecker A is a really bad sensing matrix, and I have like a section in my poster which kind of goes through why it's a bad sensing matrix. Like essentially the RIP properties are not satisfied, and if you want like the Gordon's escape through the mesh theorem does not work because the kernel of this operator is like very messy. So it's a pretty bad sensing matrix, but you can still ask whether the sparsest X such that AX A transpose equals your observation recovers the right matrix, right? And you can ask this question, and it turns out that this won't work. It's because there are some inherently bad sparsity patterns. For instance, like let's consider this X matrix, where you have a diagonal, and I always assume that the diagonal is non-zero because covariance matrices have non-zero diagonals, otherwise they are sort of trivial-ish. So, and then what we have is a vector, a red vector I'll call this, and that just forms this arrow shape, right? So because it's symmetric, this is the same as this. Now let me add a black vector which is in the kernel of A to this red vector and create another matrix that looks again like this. So this vector is just that vector plus kernel vector. And what happens is these two have exactly the same Y evaluations. So you can never tell these two apart from just looking at AX A transpose. So there are inherently bad patterns. So what we started thinking about was something that's more nuanced, which we call distributed sparsity, where we call this matrix D distributed sparse if every row or every column has exactly D non-zeros, okay? Or at most D non-zeros. So it turns out that this has very natural interpretations, right? Like for covariance matrices, all this is saying is that every variable only depends on a few other variables, and this is like a notion of structure in the data. And for graphs, it just means that the graph is bounded degree, okay? And I should note that this assumption has been studied a lot in like, say the landmark paper by Bickel and Levina, for instance. So this is like a common assumption for sparse covariance estimation. And what can you say? So we have so what I did was like, for so long I've been telling you all the reasons why you shouldn't try this, because it seems like A Kronecker A won't do the right thing and things like that. There's sparsity patterns that kind of like hurt you. But then I did like this proof technique that is tried and tested, which is MATLAB. So I just like hooked up CVX and I coded it up, and it turned out that it works. So now I had to like scurry around trying to find out how to prove this, right? So I'll go a little bit into the proof details, but not too much. There's some pretty pictures in the poster and some here, but I don't know how much I'll get into. But the basic idea is that we have the following theorem, and I'll try to kind of extract the important information here. And the first thing is, like, suppose X is D distributed sparse. Recall that just means X looks like this. It is, so if you pick up a sparsity pattern at random, then it will look like this. I don't want to like quantify that more precisely, but you can prove something like this, that it will look like that. And if A is chosen in a particular way, I'll describe that also later, then what you have is X can be recovered exactly. So you have this sparse matrix that can be recovered exactly from solving this very simple L1 minimization, okay? And I've been saying that this sort of is not compressed sensing where the results all look like that. But one main difference is that recall that this sparsity patterns that we're considering are extremely non-trivial, right? Like these are, I'm saying that every row and every column has D non-zeros, but thankfully I don't have to include that in the constraint. So if I had to, then I wouldn't know first how to program it, and second, I wouldn't know how to prove it. But thankfully, even if you don't include that, everything works out. The second thing is this other guy, which is we quantify the sketch dimension. So how short can you make this sketches? Like how much compression can you achieve, so to speak? And that is like square root of dp times log p. Let's do like a back of the envelope calculation. If you have like at most d non-zeros per row per column of this matrix, there are on the order of dp non-zeros in this whole thing, right? And the number of measurements you make is the size of y, or ax a transpose, which is here, and that's on the order of m squared. So if you have like m squared is less than dp, then you're hosed. Like you can never hope to recover something because you don't have enough number of linear equations. And what we show is like with a log p oversampling, you can get the right answer, and the right answer comes from a linear program. So that's really nice. And of course, like we started with a covariance matrix estimation, so I abstracted all this away. So I want to bring it back to when you have some noise. So suppose you have like x hat, which is x plus some noise matrix. Then you have similar results, except you have this sort of robustness guarantee that the solution you recover is away from x away from x at most by a quantity that is determined by the noise. So, and notice that if I let n go off to infinity, which is the number of samples, then this capital N goes to 0, and we get a consistent estimation. So what will be really cool, of course, is that if we can quantify the sample complexity. We have not done that. I think, well, that's like a definite next step. So yeah. Now, the one thing that I promised that I'll tell you guys is how do you pick A, and I've been kind of like skirting around this for a while. And the choice of A comes from this nice paper by Daring et al. And what they say is if you pick A to be an adjacency matrix of a bipartite graph. What's a bipartite graph? It's just you have two sets of vertices and edges only go from this side to this side. There are no edges between groups, like within groups. And if you pick like left regular, that just means that the guys here all have the same degree. So if I pick like the adjacency matrix of A to be the adjacency matrix of left regular bipartite graphs, then these have really good properties. That these are expanders for it. So this is like a catch-all term for nice graphs, and or not nice if you care about those things. But for these settings, expanders are really nice. And what they also show is that expansion for these kind of graphs is equivalent to the so-called null space property, which is what compressed sensing people use to prove that their algorithms work. So null space property is known to be equivalent to what you want. Like you want to recover sparse vectors, then the null space property needs to hold. And they show that this particular thing holds. But again, like a chronic array doesn't have this property. So it turns out that a chronic array has like very poor expansion properties. But what we were able to show is that if your support set looks like a distributed sparse support set, then you can get like a sort of expansion property, which we call this like distributed expansion. And I think in the paper we call it weak distributed expansion, because it's not quite expansion, but then if you do the right thing where everything is sort of unbiased, then you get like a nice expansion here. And there's also like, we need something called small crossover, but all these things are details that I'll leave it to interest your audience for talking later. So we ran some preliminary experiments where, so here is the number of variables, like this P, and P is so now you have a P by P matrix, so it's a smallish experiment. And this is the sketch dimension. This is how much you're compressing each of these vectors. And if you see, like, the black region is where recovery fails. So it fails, really fails. And I don't know if you can see, maybe you can't see this, there's like a grayish dot there. So there's like some randomness going on. But then it's pretty stark, right? There's this region where recovery fails, and this region you get exact recovery. So, and if you look at this line, which, I mean, I've not done the scientific way of like actually fitting the curve, but it looks like what the theory predicts, which is that the number of variables is like the number of dimensions squared, roughly speaking. So this sort of confirms what we observe. We don't have like phase transition results, but this is pretty good evidence for that. So what's the takeaway? We have introduced a framework for thinking about pooling for statistical data. I think this becomes really important when you have like big statistical problems where you can't do all these huge experiments and you want to think about how you can group experiments and do them together. And of course, on the technical side, we have like nice theory to handle things like achronic array. This lets you build like big sensing operators from small ones, and it also like we have some like I showed you, we have some combinatorial properties for tensor products of expanded graphs, which may be of independent interest if you're that kind of person. So, and the current efforts are like I said, if you how do you make sigma robust to Wishart noise? What that means is that if you really have a sample covariance matrix, then the noise can be considered to be Wishart, and you can sort of the goal is to quantify what happens there, like what's the sample complexity, what does n need to be, and we suspect that there's something non-trivial going on there. And the other thing is A I picked to be 0, 1, and there was a very good reason for that because 0, 1 matrices capture pooling very nicely. Like if you say I look at the row of this A matrix and it's 0, 1, it's 1 in like say 3, 5, and 7. All that's saying is take the third variable, fifth variable, and seventh variable and pool them together. So it does nice interpretations, but maybe some people care about Gaussian sensing matrices, and we want to extend this theory for that. And the more challenging part yet is that if sparse covariance matrices are only that useful, sparse inverse covariance matrices are way more useful, and frankly speaking, this is the problem we started with, and then I did the usual trick of like making the problem simpler, and I looked at sparse covariance matrices, which turned out to be not that as easy as I expected, but it's much more tractable. So we are looking at now recovering Markov structure, which is sparse inverse covariance matrices from sketch data. So, thanks. And the archive paper is there. Yeah, so.
What happens if you use multiple A's? Can you do that?
This says you don't need to because we sort of show that